Hi guys, welcome back to the channel. In this video we are going to discuss about flip-flop conversions. So this is the second part. In the first part we have already discussed about SR to other remaining 3 flip-flops. In this video we are going to discuss from JK to remaining 3 flip-flops. So let's get started. So this thing that I have mentioned in the previous video, there are total 12 types of conversions. So from SR to remaining 3 flip-flops that we have covered in the previous video. So if you miss out that video, I am giving that video in the description box. Please check it out. So today we are going to see from JK flip-flop to SR flip-flop, JK to D flip-flop, JK flip-flop to T flip-flop conversion. So let's see how to do that. So starting with JK to SR. So before that we need to understand some flip-flop conversions. So for that conversions we need to have some basic idea of these rules. So we have already discussed in detail in the previous video, but just in brief we are going to see here also. The first step is to draw the truth table of the required flip-flop. So in the first case that required is the SR. So we will see that also. So the next step is to draw find out the excitation table of the JK flip-flop. Means here we are going to convert from JK to others. So we are going to have JK excitation table. Next make K-map. Next draw the last what is draw the logic circuit. So let's implement with the actual thing that you can able to understand. So the first step is to draw the truth table of the required flip-flop. So here is our required flip-flop is SR flip-flop. So we are going to have the truth table of the SR flip-flop. So the present state Qn, the next state Qn plus 1. So I hope you know this about SR flip-flop. So if you don't know, I am giving the video about SR flip-flop in the description box. Please check it out. And I am also taking extra 2 columns, that is JK. So we are going to fill this JK using the excitation table of JK flip-flop. So if you see clearly, the Qn is the present state and Qn plus 1 is the next state. So the each and every transition have some values. So if you see in the last two case means Qn plus 1, that is don't care conditions. In the next state of the SR flip-flop, in the truth table that we already know. So according to the transitions, and we are going to compare in the excitation table transitions also. So again from the transition table we are going to fill this JK columns. So this is the excitation table of the JK flip-flop. So we have in the JK flip-flop Qn plus 1 and JK. So we are going to have the things from 0 to 3, that is 0, 0, 0, 1, 1, 0 and 1, 1. So correspondingly we are going to have the excitations as JK as 0, don't care, like that we are going to have this excitation table. So if you want about more details about this JK flip-flop excitation table, so you can check out this video. This video is very important about JK flip-flop explained very clearly in this video. So basically an overview of excitation table means, so the outputs and inputs should be there. So for what output transition, the input corresponding input would be there. So that is the basic excitation table thing. So if you see the transitions from Qn to Qn plus 1, the corresponding inputs are there. So explain detail in this video, JK flip-flop video. So if you know, let's get forward. Now we are going to start filling this SR truth table with the help of this JK flip-flop excitation table. So if you see for the first excitation from Qn to Qn plus 1, we have 0 to 0. So the same excitation in the excitation table also we have to compare, and we have to fill JK as it is in the SR table, truth table. So if you observe, that is 0 don't care. So fill directly 0 don't care in this table. That's JK directly. Next transition, if you observe from Qn to Qn plus 1, that is 1 is changing to 1. So in the excitation table of JK flip-flop also you can also see that same case, that Qn is changing to Qn plus 1 as 1 1. So place that JK as same as that don't care 0. So I hope you can fill the same things remaining likewise. So you have to stop up to you see the last last third case, that is 1 is changing to 1. So the case is again don't care 0. The remaining things I hope you can fill out by seeing this excitation table of JK flip-flop. But the last two cases we don't know. What is we are changing to don't care situation. So in that situations we are going to have the JK outputs or the inputs as don't care situations. So as I am showing there, just fill out that JK columns as don't care for the last two situations. So after filling this whole SR flip-flop truth table including JK columns, you are going to trace out the K-map. You are going to have the K-map of this. So you are going to have the K-map of J separately, K separately for S, R, Q. So basically we have 3 variables, that is S, R, Qn. So we should not consider Qn plus 1. We should only consider S, R and Qn. So we should have 3 variable K maps. for J and K. From that we are going to have Boolean expressions of existing flip-flop means JK flip-flop only. So let's see how to do that. So you are going to have the K maps in this format. The first K map is corresponding to J, the second K map is corresponding to K. If you observe corresponding to J, we have the min terms in the position of 4. So I have highlighted in the black color also, segregated as black color. So if you observe the remaining don't care situations, we have in the 4 places we have don't cares. That is 1, 3, 5, 6. I am just talking about J column. So fill this all the min terms on don't care situations in the K map that you can also observe there how I am taking. So the variables are S, R and Qn. So we have 3 variables. So we should have 8 means 3 variable K map. So we can make group of 4 elements as you're seeing there, including don't cares 4, 5, 6, 7. So simply J is equals to S. The output expression is J corresponding to S. So if you see for the K also you have min terms 3 don't care situations in the positions of 0, 2, 4, 6, 7. So I made as group of 4 elements. So the K output expression is similar to R. And the last step remaining is just we are going to have this J, K and in the circuit diagram. So let's see on the block diagram as well. Finally, we are going to have the JK flip-flop to SR flip-flop conversion. So for that we need to have the JK flip-flop. So in this we are going to have the inputs as J is equal to S, K is equal to R. Means in the K we have already K line. In that we are going to pass R. Already we have the line J. In that we are going to pass S. So this is the SR flip-flop conversion. Implementation of SR from JK. So this is the thing that I am saying about. Finally, means the JK flip-flop is converted to SR flip-flop. So if you pass JK in the place of JK, if you pass S and R, that becomes our SR flip-flop. So both SR flip-flops are same. So now you might think, then what is the reason of having the JK flip-flop? So simply pass S and R only in that. Then why we need this whole conversion? You might have that doubt. So unfortunately we just got this logic, so that is the reason that we are simply passing S and R in the J and K. If we might got some logic, other logic, then we have to pass that logic as well. So the situation is simple. I hope you can understand this conversion. So the next conversion is from JK flip-flop to D flip-flop. So in this scenario we are going to have the excitation table. So the excitation table is very important. For this video the JK flip-flop excitation table is very important. Because for every conversion we are converting from JK to D, we are converting from JK to T, so that we are going to have the JK flip-flop excitation table. So what we are going to build? We are going to build D flip-flop. So as we are going to build D flip-flop, we are going to have the truth table of D flip-flop. So I took the D flip-flop truth table. So you can see, observe over there, we have the present state and next state of D flip-flop. I left 2 columns for J and K. So we already know what is meant by D flip-flop. In the D flip-flop we know that D and QA plus 1 will be the same. So that is the basic property of D flip-flop. D and Q plus 1 would be the same, whatever may be the Qn. So the same thing that we are going to follow here also. We are going to compare the JK means the QN plus 1 here and the excitation table. The first excitement would be 0 don't care, fill directly by seeing the excitation table of JK flip-flop in that D flip-flop truth table. So in the same way we are going to fill the whole J and K columns by seeing the excitation table of JK flip-flop. So now we are going to highlight the J and K columns, the min terms, and we are going to have the K maps and we are going to solve that. So let's see how to have the K map. So finally, as we have only 2 variables, that is D and Qn. So once again I am saying, so we should not consider the next state output, that is Qn plus 1. So that is our main final output that we should not take. So we should have consider here only 2 variables, that is D and Qn. So we have 2 variable K maps over there for two variable K maps, because for J is 1, for K is 1. So if you observe the J, we have min terms 2 don't care situations in the 1 and 3. So fill that and make group of 2, 3 as a single group, that is J is equal to D, we can have output. For the K column you can see we have min terms in the 1 and we have don't care situations in the 0, 2. So we can make group of 0 and 2, that is D bar. So simply have output expression K is equals to D bar. So in the same fashion we have already got the output expressions. So J is D simply and K is D bar. So you can also observe there, the first one is our implementation with the help of JK flip-flop. So this logic is equivalent to the D flip-flop. So both are same, the logic would be the same, but for the first one we are implemented with the help of JK flip-flop. That is the main condition we had for this video. So the next conversion is from JK flip-flop to T flip-flop. So T means toggle flip-flop. So we already know what is meant by T flip-flop. So T is nothing but when T is equals to 0, the Qn plus 1, the next state would not be changed as the previous state only. It will be conditioned as whole condition. So when T is equals to 0 only, the present state, the Qn, would be toggled to the next state, that is Qn plus 1. You can also observe over there. So again we are going to have the excitation table, and we are going to fill out at the same column J and K by seeing that. So 0 for 0 0, we are going to have 0 don't care, fill the direct condition over there. So we have already solved twice. So fill according to J, K from the excitation table similarly. After filling that, you can see like this. So again we are going to have the same situation, that you are going to make again the K maps and solve that. So finally, if you observe there for J and K, we have two variable K maps, because in this case also we have having two variables, that is T, Qn. So if you observe, I have took T, so and Qn in the two variable K maps as two variables. So if you observe J, min terms are in the position of 2 and don't care situations are in the 1 3. So fill out that, and we are going to have output expression J is equal to T, and for K expression you are going to see that the same thing. So we have min terms in the 3 and don't care situations in the 0 2. So after filling that, make group 2 and 3. So output expression K is equal to T. So if you observe one thing, J and K are same, that is T only. So for this situation, we are going to merge as a single input both of them and name it as T variable. So this is the circuit diagram. I can say that. So by merging J and K, you can have the JK flip-flop to T flip-flop conversion, or we can simply say this is the main logic of the D flip-flop that we can implement. Or we can simply say that JK flip-flop to T flip-flop conversion is this. So finally, I hope you understood this video. In the upcoming video, we will be seeing that D flip-flop to other 3, T flip-flop to remaining 3. Thanks for watching up to now.